Full screen, right?
Yeah.
Yeah, sure. Let me also test. You can see, huh?
Yes.
Okay,
Yes.
good. Okay, I'm ready then.
Yeah, great. Perfect, then.
Yeah. How is your life, Purvita?
It's going on. It's just like lockdown type. It's not lockdown proper, but yeah, it's
Okay.
a situation. How about Japan?
Yeah. Now the number of infected people in particular Sapporo is increasing, so it's a bit scary. So now the level is somehow going down to 1, but now going up to 4. So
Okay.
yeah, emergency level. I mean.
Because the winter is approaching, I think everywhere.
Yeah. That's right. So yeah.
And everyone is guessing the second phase, I guess.
Yeah. And I think Sapporo has now in the third phase. Yeah. First phase was in the last February. So
right.
Yeah, I also realized that the number of infected people in India is also decreasing now, right?
Yes.
No, recently it has started going up again.
Oh, really?
Yeah.
Okay. Yeah, this morning I checked the number in Google. Then
actually, I saw in Google it's decreasing, but in our like neighboring places it is not at all decreasing. We can see.
Yeah. Sure.
Maybe the hospitalized case is decreasing, but people are in the own home, and it becomes like the normal flu or something like that. People are considering like that in some. So I'm doubtful about the number of cases for sure.
Yeah. Sure.
So your university is in online mode right now.
Yeah, still I'm going to the university. Not locked down. I mean university, but my teaching is all online.
Right.
Yeah.
So students are not coming to the campus.
No. Sorry. Some students came because actually the number of infected people is decreasing in the beginning of September. Then the university decided to welcome students back to the university. Then now the number is increasing. So
Okay.
That's the thing. So still students are in the university. And the last week I received the news. Five students are infected.
Oh my God.
Yeah. Oh my God.
Sujata is here.
Yeah. Sure.
I don't think we can hear you, Sujata.
Yes. I think there is some problem with the microphone. It's on.
Yeah, she left, I think.
No. She is there.
Oh, she's here, but yeah,
hear me?
testing.
Yeah,
Yeah,
now we can hear.
Yeah.
Hi, Katsuhiko. How are you?
Hi.
Sorry, I think I have some internet problem, so I will put my video off.
Right.
So will it be fine, Katsuhiko, if someone will ask you the question in between? Like.
Yeah. That's also fine. Yeah. That's also fine. So roughly, I prepare my the length of my talk is about 1 hour. So
Okay, that's
yeah.
Okay.
Yeah.
So did you already have dinner?
Yeah, I finished dinner. So because the time is now 8 in Japan. So
8, right?
yeah. If you try to take a dinner after the seminar, maybe it's a bit late. So I also gave dinner to my daughter. So
by 8 o'clock is the natural timing for dinner.
You mean
like finish by 8 o'clock?
Okay. So but maybe in Japan, dinner time is 6 or 7. So
okay. It's just like European culture.
Yeah. I don't know, but from my personal experience, so I usually take dinner at 6 or 7. So
like for us, it's the snacks time, and then dinner somewhere in 10 or something like that.
I see.
Oh, Akilda is there.
Yeah. Ananta had joined.
Yeah. Akilda and Katsuhiko is very good friend.
Yeah. I'm glad to. Yeah.
Hi. How are you?
I'm fine. So
great.
Now my baby become 1 year and 2 months. So
2 months. Okay.
Yeah.
Turn up.
Yeah.
I just wanted to say hi as well.
Yeah, hi. Nice to see you. Lam. How about you, Akiru?
It's fine.
How
Semester.
How?
Yeah. You want to say something?
Yeah. How old is your daughter now?
No, I have 2 sons.
Sorry.
One is 11 years old and other one
11
is
years old. Oh,
6.
yeah. Okay.
Other one is 6 years old.
Okay. Yeah. I remember I saw the big picture of your son in Amsterdam. So at that time, very small. So that's almost 10 years ago. So now I can calculate.
For you, they are still the little one. It's already 10 years, yes.
Yeah, already 10 years. Yeah. I also met Purubita 10 years ago.
So in Japan, you are taking classes. All the classes are online. Or,
Yeah. Some professor prefer to have a lecture in face to face, but for my lecture, they're all online. So.
Okay. So here same thing, but I'm teaching this BTech course this time. So 250 capacity.
250. Oh, wow.
And then conducting exam for these students, I'm finding a little difficult. Online exams.
Yeah, that's really fun.
And where are you, in Kolkata or in Indore?
Indore.
You came back.
Yeah, came back. What about IT Kanpur? How you are managing exams?
Online. I mean, fortunately, I have got a small course of 5 students.
Okay.
So yeah, everything is manageable right now.
Yeah, manageable. Number 5 is manageable.
One particular problem I am facing whenever we conduct exam, more than half of the students say that they are having internet connectivity, they need more time. And when we give more time, then we see the answer, it's a copy paste from the other student.
Correct.
So we don't know which are the genuine cases where, who has really faced the problem and who are misusing this. So really is becoming difficult. And 250 student, keeping track to them, it's also not so easy.
Not easy, correct. Okay, shall we begin?
Yeah.
Sorry.
I think.
Oh, sorry. What? No. Sorry.
We already saw all the slides.
No. Mistake. Yes.
Okay. So a very warm welcome to all for this logic webinar by Professor Katsuhiko Sano from Hokkaido University. After completing his PhD from Kyoto University, he held various positions in ILLC Amsterdam, then University of Leicester, and Japan Advanced Institute of Science and Technology. His research interests are in semantic and proof theoretic studies of modal logic and non-classical logic. So, yeah, over to you, Katsuhiko.
Thank you very much. So it's my great honor to give a seminar here. So I have a lot of Indian friends. So and I met Pulubita and Akil 10 years ago, and since then I also met Sujata and Ram. So I'm very glad to give a talk here. Anyway, then let's start. So today's topic is a Goldblatt-Thomason theorem for non-classical logic. So maybe you may heard about the term Goldblatt-Thomason theorem, but I will explain what is the theorem. Okay. So this is the outline. So in the first part is somehow high-level presentation of what is a Goldblatt-Thomason theorem. I'd like to introduce several Goldblatt-Thomason theorem for modal logic, graded modal logic, and modal logic with universal modality, and Goldblatt-Thomason theorem for intuitionistic logic. Actually, I want to talk all of them, but time is limited. So today I want to focus on the intuitionistic logic. Intuitionistic logic is a Goldblatt-Thomason theorem for that is less well known, but intuitionistic logic is very important. So I choose that topic as intuitionistic logic. So, and from the second section, I start from the definition of syntax, semantics, and provide Goldblatt-Thomason theorem of intuitionistic logic and the intuitionistic logic with universal modality. And the third part is somehow intermediate result. The somehow goal of this talk is in part 4, intuitionistic inquisitive logic. Maybe you may heard about the term inquisitive logic. So basically, the idea of inquisitive logic is we want to capture the notion of question in the setting of classical logic, but they also extend it to the intuitionistic logic. And I want to, and my purpose is I want to give a Goldblatt-Thomason theorem for the intuitionistic inquisitive logic. And for that purpose, I want to use the results of part 3. So basically, this is the outline. And I forget to say that, but if you have any questions, so you may, I don't know how you ask question, but you may raise hand, and then I hope the organizer may catch catch it. Yeah, okay. So then let's go into the detail. So, okay. Yes, and the first part. Oh, sorry. No. So this part, okay. So I think most know about this correspondence theory in the modal logic. So I put a very well-known formula. Here is a model formula. First one is axiom T, right? Second one, axiom B, axiom 4, and axiom 5, and axiom D, right? And all of us, I hope, know that each formula defines nice foreign property: reflexivity, symmetricity, transitivity, Euclideanness, and seriality. So then usually we can say that this formula say this box P imply P correspond to or define reflexivity. But what's the meaning of correspondence or such a definability? So yes. So this is the definition of definability. Gamma is a set of formula. This gamma defines a class F of Kripke frame. Say, for example, you may take a class of reflexive Kripke frame. Then the gamma, but here box P imply P is valid in F if and only if F is reflexive for all Kripke frame. When we have such an equivalence, we can say set of gamma defines a class of class F of Kripke frame. So now let's see. So then the question here, let's see. Question here is the following. So here we can look at such a nice property, right? So this is a nice property, and you may realize that this is all these these are first order property, right? So we have a universal quantifier and a binary relation. So we can write these as in the first order syntax. So then question here is which kind of first property are definable by a set of model formula? So that's a question of model definability. Let's clear this. Okay. So then the Goldblatt-Thomason gave an answer to such a question in 1975. So let us denote ML is a basic model language. And here I put the term. So elementary here means the first order definable. But here we have in the first order syntax we allow the binary relation and the equality. This is just a parameter of the language. And first order definable means definable by a set of first order sentence with this signature. Okay. Then there's such a elementary frame class F. So reflexivity is an example, right? Transitivity is also example. Such a frame F is modally definable by a set of model formula if and only if F is closed undertaking bounded morphic image. So for the time being, you may regard this is just a kind of homomorphism. And the generated subframe, this is somehow you may regard this is the kind of subset operation taking subset of Kripke frame. And disjoint union. Disjoint union means that you may paste frame or Kripke frame side by side, or you may also regard this is an addition of Kripke frame. And it reflects. Reflects here mean that this is F, right? Reflects means this F complement. So this is complement. Complement is closed. Complement of F is closed undertaking ultrafilter extension. Ultrafilter extensions means if we have a Kripke frame, and the Kripke frame can be viewed as a model algebra, right? Then for the model algebra, we can consider the operation of completion. Then that kind of completion is ultrafilter extensions. Today, I will not go into the detail of ultrafilter extensions, but we will see the similar notion of prime filter extension in the setting of intuitionistic logic. Anyway, so and actually this theorem is proved by using algebraic method by Goldblatt-Thomason. That is, they use the duality between Kripke frame and the modal algebra. But later, the important proof is given by Johan van Bentham, 1993. The nice point of his proof is did not use any algebra, so purely model theoretic proof. So advantage of this proof is so basically algebraic proof need to have kind of duality result, but the van Bentham the proof does not require such a duality. So with a duality we can get the result. So this is a nice point of Johan van Bentham's proof. Okay, so yeah, so then we may also consider the graded modal logic. This is the modal logic with extended with graded modalities. So for any natural number, we introduce such a operator indexed by k. So at W, so meaning of this is at W, this diamond greater than or equal k phi if and only if there are at least k phi successors. And so if you prefer the mathematical definition, you may also write this is somehow similar. So all the successor and the true set, then the cardinality is greater than or equal to k, right? Somehow we can count the number of successor. For example, Kit Fine give the completeness proof of this kind of logic. And actually, so this is my result. When I was in Amsterdam, I met my friend Ma Mingwei, and I and Mingwei Ma and Akio had a regular meeting on logic. So, and at that time I wrote a joint paper with Mingwei Ma and graded Goldblatt-Thomason theorem for graded modality. So the idea is proof is the following. Statement is the following. Elementary frame class F is graded modality definable if and only if F is closed undertaking G-morphic image. I will not say the detail, but this is I can add a modification to counting the number of successors. So that the result is that G-morphic images generates subframe and adjacent unions. I also need to change the reflection part. Instead, the reflection ultrafilter extension, I need to add the graded eumorphic images. So this is my result at the AIML 2010. So, but the nice thing of such a Goldblatt-Thomason theorem is we can capture the expressive power for the elementary frame class in terms of the frame construction, or roughly we can say that we can see the expressive power in terms of the geometric construction for the Kripke frame. So this is very, very, very nice point. Yeah, so, and you may also know that for the algebra, right? So it is also well known that a class of algebra is definable by a set of equation. Then that class is closed undertaking homomorphic image and subalgebra and products, right? So that's a Barkov's variety theorem. So somehow Goldblatt-Thomason theorem is a dual version of Barkov variety theorem. Okay, so then maybe we can go next. So I will not go into this result, but if you are interested in, please, you may also send me any email. I can give you more detailed information on this theorem. Okay, so yep. So then, but let's look at the goal. Yeah, sure.
Question.
Yeah,
so
yeah.
In the first order logic, is equality included in the syntax?
Yeah. Sure. Yeah, equality is necessary. Yeah.
Okay.
Yeah.
So the syntax of the first order logic has equality in it.
Yeah, equality has equality. Yeah, that's the same definition. So if you look at the modal logic textbook, right, by Blackburn, so there we can find the notion of first order frame language. First order frame language contain the equality. So I also assume the same syntax.
Okay, thanks.
Yeah, sure. Yep. Okay, so this is the Goldblatt-Thomason theorem, right? So then today I want to consider different extensions than graded modal logic. So this is maybe this is also familiar extension of modal logic with universal modality. Universal logic means that we can W forces A phi if and only if everywhere phi holds. Then you can see intuitively this gives us a more expressive power, right? So then actually this is captured by the following closure condition. So Goranko and Passy actually prove the following result. Elementary frame class F is closed is definable by a set of modal logic with universal modality if and only if F is closed under the bounded morphic image. But now we lose closure under disjoint union and closure under generated subframe, but we can still keep reflection of ultrafilter extensions. So then next. Then this is somehow intermediate result actually. So in this syntax, I just allow the positive occurrences of universal modality. I don't want to put the universal modality under the negation. So then I can get the following definability result. Goldblatt-Thomason theorem, elementary frame class F is definable by a set of modal logic with positive universal modality if and only if F is closed under the bounded morphic image. Now we can recover generated subframe, and it reflects a complement of F is closed under the ultrafilter extensions. But I need to do one more finitely generated subframe. I will explain what does reflection of finitely generated subframe mean in a later. So, but you may wonder why I wanted to have such kind of result. So let me explain. So this is related to the topic of model dependence logic studied by Väänänen in 2008. So according to Väänänen, so model dependence logic, logical modeling of uncertainty, imperfect information, and functional dependence in the framework of model logic. So and I will give you an idea of model dependence logic. So here I just write a very simple truth table, right? You may also write such kind of truth table in elementary logic course, I think. Then yeah, this is just I write a truth value. Oh, I write all the possibility. Then, for example, if we just focus on the say W1 and the W3, right? W1 and the W3. Now we can say that if we focus on, and I want to regard this is input, this is output, right? This is output. Then if we just focus on W1, W3, right? So if we input is 1 and if we input is 0, then we can get the output are 1, right? But this means that if we just focus on W1 and W3, then we can regard such a correspondence as a function, right? So in that sense, we can say the truth value of P functionally depends on truth value of Q. So, or truth value of Q functionally determines truth value of P, okay? But so that's the idea of dependence atom. Yeah. So if we focus on W1 and W3, right? W1 and W3, it becomes there's a dependency, the sense I said to you. But if we focus on the W1, right? W and W2, right? Then in this case, so input is 1, right? But somehow value is undeterministic, right? So then we cannot say there is a dependency. So this is the idea. And I want to say one thing. And if you see any singleton, right? Any singleton behave like function, right? So here I focus on W2, right? Then this is function, right? So this suggests that if we focus on, so if we want to capture such a dependency, somehow we need to lift our semantics to the state-based semantics into such a semantic based on sets of points. So this is the idea of capturing dependency. So and they say that this is CHIM semantics. So somehow we need to lift previous semantics in the CHIM level. Then we can somehow capture such a dependency. And they say that such a set of points are CHIM. So and later we will see CHIM semantics for intuitionistic logic. Okay, so then what I did is this is actually originally published in the Warwick and later published in the journal Apple. And what I did is we realized that this model logic with positive reversal modality has the same expressive power for the model logic with dependence atom. So by using the model logic with positive reversal modality, we provided the Goldblatt-Thomson theorem for the model logic with dependence atom. So this is somehow what I did. Then let us now move on to the correspondence theory of intuitionistic logic. So the definition of definability is the same. So but the intuitionist Kripke claim. So you may this is just a pre-ordering. This is pre-ordering. Then for example, law of exclusivism define the symmetricity, and this is the weak. This second one is a weak law of exclusivism defines somehow the directedness or Church-Rossa property. And the final one, this is called the Gade-Damet formula. Gade-Damet formula defines light connectedness. Yeah. So if you have such V or U, you may you may have here, or you may have here. Yeah. So light connectedness. So we can then we may also ask the same question as in the modal logic, right? These properties are also first order property. So then what kind of first properties are definable by using intuitionistic formulas? So then the answer is given by the Peter Hendrik Rodenberg in 1986. In the book whose title is Intuitionistic Correspondence Theory. Actually, this is the PhD thesis at the University of Amsterdam, defended on the 5th November, and the promoters are Anna Trullustra and Johan van Benten. And this is the Rodenberg result, elementary frame class F. So here mean the elementary frame class is now we correct the class of pre-ordering is definable by a set of first order sentences. But now we assume R is reflexive and transitive. And such a frame class F is indefinable if and only if we may keep this part. We can just get a bounded morphic image generated subframe and disjoint union. But now we need to change this part. Previously we have ultra filter extensions, but now we need to have a prime filter extension. So this is somehow very similar to when you want to prove completeness theorem modal logic, you construct a maximal consistent set, right? But if we look at the intuitionistic logic, canonical model is defined in terms of the notion called prime series. So this is somehow semantic version of canonical model construction of intuitionistic logic. Anyway, so then what is intuitionistic inquisitive logic, right? This is an attempt to add a notion of question in the setting of intuitionistic logic. And this is proposed by Ivano Chaderi, Rosalie Yemfov, and Fan Yang in the 2020. And this paper is recently published in the Notre Dame Journal of Formal Logic. And the title is Questions and Dependency in Intuitionistic Logic. And in order to capture dependency, as we saw, so we need to change our semantic set-based, state-based semantics into the scheme-based semantics. And in the final part, they ask the following question. It would be also interesting to look at the issue of frame definability of inq-I. Inq-I, so here, inq-I, right? Inq-I means the intuitionistic inquisitive logic. And the recent work on frame definability in the context of model dependence logic, so this is my joint work with Joni Wiltema, might provide a handle on this question. So I regard this as a challenge to me and Joni Wiltema. So I try to answer. And the actual answer is yes, and I published this result in this year's AIML. And the inq-I is let inq-I is an interesting logic with inquisitive disjunction. So this is special disjunction. Later I will explain the semantics. Then this is very similar to my Goldblatt-Thomason theorem for model dependence logic. Just one part is different. So this part, right? Previously here we have a ultra filter extensions. Now we can just change this part into the prime filter extension. I can get the result. Then similarly to the modal logic case, what I need to do is somehow I want to use the somehow detour using intuitionistic logic with universal modality. So this VA int means disjunctive A clauses, and here this VA is yes. So intuitionistic formula plus universal model and disjunction. Then first I prove this result. Then after that I provide a Goldblatt-Thomason theorem for the
Katsuhiko?
Yeah.
Could you please let me know, like, why this ultra filter extension is not capable to think about this join definable?
So I mean, so considering so you know that so definition of ultra filter extension, right? So definition of ultra filter extension,
It's
F is filter, right? And for any set, X belongs to filter, or complement of X belongs to filter, right? So this is actually somehow correspond to lobe exclusive middle. So if you want to consider intuitionistic logic, we cannot use that. So instead, we just require that the disjunction belongs to, or union, right? Union belongs to the filter. Then one of the components belongs to the filter. That will be enough. So that's the core of prime filter extension.
Okay. Thank you so much.
Yeah. So somehow this is intermediate result. So yep. Yeah. So first part is somehow high level presentation. So I did not tell you all the definition on the details. So but now I give you all the definition and detail. Yeah. Okay. So far so good. If you have any question, you can ask me. So far so good. Okay. Okay. Right. So then let me go into the second part. Okay. So this is syntax. So maybe this is very easy, right? So usually propositional logic, but negation is defined fine prime bottom. And I also defined a syntax with universal modality. I just with operator A here. This is very, very easy, I think. So yeah. Then semantics. So maybe some of you may not know much about intuitionistic logic. So let me say a small thing. So introductory thing. So usually we can say that intuitionistic logic plus lobe excluded middle is classical logic. So some people may say that from classical logic we subtract lobe excluded middle, we can get the intuitionistic logic. So inventor of intuitionistic logic. So this is L.E.J. Brouwer, and this is actually a stamp in the Netherlands. So anniversary of 100 years old of L.E.J. Brouwer, and you may see that here L.E.J. Brouwer is a dislike lobe excluded middle. And actually Brouwer somehow some statements are undetermined. So for Brouwer, but why does he wanted to have such a strong opinion? So let's see. So here is the somehow heuristic motivation written by Van Dalen in the book of Logic and Structure, 5th edition. So let's see. So think of idealized mathematician. In this context, tradition called creative subject. So Brouwer considers such a creative subject, but we may regard this is an idealized mathematician, and who extends both his knowledge and his universal object in course of time. So today we can just concentrate on knowledge, because universal object is related to the quantifier. And at each moment, he has a stock of sentences which he, by some means, has recognized as true. So idealized mathematician is doing proof, right? And once he prove it, then that mathematician is idealized. So he will not make any mistake. So this is the idea. So for example, So here, I'm not good at writing a picture, but here, ideal mathematician writing a proof, right? And in this moment, he proved P, right? Then this proof doesn't contain any mistake. So this is continue to be true. So this is the idea. And the next, this guy, in this state, he did not prove Q, but here, finally, he proved Q. Then this proof doesn't contain any mistake because he's an idealized mathematician. So this will continue to be true. And this continue to be true is called the idea of monotonicity or persistency. Okay, so then now I can give you the definition. So M is an interesting Kripke model. If W is non-empty and R is pre-ordering. So you may also regard R as a partial ordering, but I prefer to have a more generalized definition. I prefer to define R as a pre-order, so reflexive and transitive. And VP is persistent. We already see the idea of persistency. So P is true at W, and from W we can access to B. Then the P is also true at B. So this is semantics. WP true if and also W belongs to P. So I think this part is fine, I think. No, very similar to modal logic. So maybe I can give you a comment on the two. This idea of implication is classically, this is a box implication. But of course, implication is different meaning. But if you know about modal logic, this is box implication. So let's see. So W forces phi imply psi. Then for any state W accessible from W, if at B forces phi, then B forces psi. So box implication. And universal modality, we can keep the same definition as in modal logic. So at W, if phi is true, if and only if everywhere phi is true. Then one nice thing is we can say that so this true set is true upset or persistent, and even if we add the universal modality, because the true set of universal modality is from this definition, we can say that this is a full set or empty set, and these are the trivial upsets. Okay, so then the validity on a flame and the definability of a flame class are defined as usual. We already see that in the introductory part. So let's just introduce two terminology. F is int definable. We can find some set of, this is the set of intuitionistic formula defines F, and F is int A definable. We can find some set of formula possibly with universal modality that defines F. So bounded morphism. So I said that this is similar to homomorphism, but actually this is the definition. So we suppose that we have two Kripke frames, WR and W prime, R prime. This is the bounded morphism. We should, then this F should satisfy two conditions. But I can give you one example. Example is easy for you to understand. So suppose that we have 2 points, reflexive, and one single reflective point. Then and if we consider such a mapping, then this is the example of bounded morphism. And actually, this is surjective, right? And you can easily see this is it satisfies force condition and also satisfy the say back condition. Back condition say that once you send it, there's a loop, but there's a mimicking move. Oh, sorry. There's a mimicking move. Yes, this. Yeah, mimicking move from here, and we can send it here. So this is back condition. So we can prove that int A definable frame class is closed undertaking bounded morphic image. So this means that if the mapping is surjective, if you have phi from formula with possibly intuitionistic logic, then we can also say that phi is valid here. So that's the content of here. Okay. Yes. Then generated subframe. So generated subframe is this is the idea here is that so this is a small flame, possibly small, and this is big flame. So small flame is a generated subframe, a big flame. If this is small, right? And the relation of small frame is just restriction of a big relation. And but generated means domains should be an upset. For example, here we can give an example. So in this picture, I omit the reflexive arrow. I omit the reflexive arrow. Then, for example, we can say this part, right? This part is upset. This part is also upset. And also, this part is also upset, right? Then, for example, in this setting, orange frame is a generic subframe of green frame. And this is also orange frame is a generic subframe of green frame. Then we can prove that. So this is the interdefinable. So we cannot add the universal modality. So but the meaning of it, phi from form is valid. Then this phi is also valid in this frame. So this is the content. Formula phi is valid in a bigger frame. Then the phi is also valid in a smaller frame in this sense. Okay. Yeah. So now I can tell you what is a prime filter extensions. So let WR be a frame or a pre-order, then define the power set up W is a collection of all upsets. Then I want to say that if this collection of upsets is a prime filter on W if and only if the collection is non-empty and the collection should not contain empty set. And the second condition is filter, right? Intersection belongs to F if and only if each component belongs to the collection for upsets. And the final condition is just I said to prove beta. So for any upset X and Y, union belongs to F, then the X belongs to F or Y belongs to F. So this is the definition of prime filter. Then the prime filter extension. So then, as I told you, so if you have looked at the completeness theorem of intuitionistic logic, so this is the semantic version of canonical model construction. So prime filter extension PEF of frame F is defined as follows. So here PFW is a set of all prime filters on W. And how we can make a relation F1 related to F2 if and only F1 is subset of F2. So, and as you can easily see, this is the reflexive and transitive. And in addition, also anti-symmetric. Then the Rodenberg, actually Rodenberg proved that without universal modality, but I checked that it can be extended with universal modality. Yeah, given frame F and the formula phi, possibly with universal modality. Formula phi is valid in a prime filter extension of F, then phi is valid in F. How I can prove that? So yeah, actually proof using the corresponding results over the model. Given any variation V on F, we define the variation over the prime filter extension of F as follows. So VP belongs to F, we collect such a prime filters. So then now we can define the variation over the prime filter extension of F. Then we can get the following equivalence. By using this variation, a prime filter extension of F and this variation, F forces phi if and only, so this true set is become upset. So this is eligible to be an element of F, and but here this true set belongs to F. By using this equivalence, we can prove this one. So and as I told you, so denotation of A phi, right? True set of A phi is full set or empty set. So by using this result, we can also cover the universal modality. Okay, so then this is Rodenberg result. So actually, Rodenberg's proof is also use a duality between Heiting algebra and the Kripke frame. But what I checked, I can also use a fundamental model theoretic argument. So core of model theoretic argument is basically compactness argument. So then I also provide the gold path of Thomason theorem for the intuitionistic logic plus universal modality. And as you can easily imagine, here we lose closure under disjoint union and generate the subframe, but we can still keep closure under taking bounded monolithic image and it reflects prime filter extensions. And the proof is basically the combination of Rodenberg argument and the van Bentham's model theoretic argument. Also compactness argument. Right. So maybe, if you are interested in logic, you may wonder what is the axiomatization of intuitionistic logic plus universal modality. So here I put the answer. In addition to all axioms rule of intuitionistic logic, we can add the following 4 axioms and 1 rule. So this is a K axiom and the reflexivity, transitivity, and this is the intuitionistic version of axiom 5, and the necessitation rule. And I realized I can prove completeness by using this result, but later I realized that actually this is the same logic as L4 in Hiroaki Ono's paper published in 1977. In this paper, Hiroaki Ono considered several intuitionistic variants of S5. So there are several kinds of S5-like axioms. So some become equivalent. These are all become equivalent over classical logic, but the intuitionistic logic, we should distinguish these. And this is the strongest logic in the setting of intuitionistic logic. And Hiroaki Ono provided slightly different semantics, but I can connect his semantics into this setting, and this axiomatization above is sound weakly complete and become decidable. I can also extend it into the strong completeness. Okay, so this is finish the third part. So far, so good. Any question so far? If not, I can continue. Okay.
Can I ask?
Sure.
Hi, Katsuhiko.
Yep.
Yeah. So you've been talking of definability with respect to frames. So what about models?
Good question. Good question.
Models.
So I will actually for the model dependence logic in the upper paper, I also provided the characterization of class of model. And for the intuitionistic setting, in the final part, I will give you one difference. Actually, Goldblatt provided the characterization of class of model. And now I'm trying to extend result also in this setting with universal modality. Yeah.
Okay.
Okay. So thank you, Mohua. So, okay. Then then let's go into the. So this is the disjunctive A clause. So this is plays a very important role. So let's recall that form is a set of all intuitionistic formula. So then I want to define the disjunctive A clauses, VA form. This is defined by the following grammar. So I want to use rho to denote disjunctive A clauses. So this is disjunction, intuitionistic disjunction. And we have a universal modality. Then after that, phi I is a purely intuitionistic formula. So this means that we don't allow the nesting of universal modality. Okay. For example, here I put the example AP or so everywhere P or everywhere not P is a disjunctive A clauses. Okay. So then what is the closure or reflection property of VA interdefinable class? So let's say that a frame class F of frame is VA interdefinable if a set of disjunctive A clauses defines F. Then the proposition is the following. So, but please recall that for this one, right? This is the we already have these results for the formula with arbitrary occurrence of A. So new thing is this one. So for somehow, if we consider such a set of disjunctive A clauses, we can recover the following. So let's D is small one, small frame. This is big frame. Then in the big frame, rho is valid. Then the small frame, rho is valid. We can say this for the the disjunctive A clauses. So, but if we allow the negative occurrence of A, right? For example, if we put a negation, and after that we have A, we lose this property. So, okay. Yeah, so this is nice. And then the next thing is the following. So then this class is not, unfortunately, this class is not closed undertaking disjoint unions, because this formula, I saw this formula, everywhere P or everywhere not P, right, defines this everywhere is reachable. How we can prove this? For example, this single reflexive point, then we can say this because everywhere reachable. So we have a P or a not P, right? And similarly, we also have this. But if we take this disjoint union, what we can get is this one, right? Then if we focus on this point and this point, there's no accessibility. So given this definability result, sorry. This is valid. So this gives us the VA interdefinable class is not closed undertaking disjoint union. Yeah, but we have very similar, yeah, bit like a disjoint union like property. So this, how I can go back. Yeah. So let me say that this property is the following. So we have frame F, right? We have frame F. So this property is saying that, so first let's say that frame G, G is, so this means that G is generated. So G has a finite generator, means we can specify a finite point and everywhere is reachable from one of them. So generator is finite. From such a finite set, we can cover the for G, domain of G. So this is a definition of finitely generated subframe. So generator is finite. A point generated subframe is also finitely generated. We may also take just 2 points. From that we can chase all the accessible state. Then we can somehow specify the generated subframe. Then that generated subframe is has a finite generator. Okay, so then what is the property? Let's clear this. The property is the following. So we have F, and then we can consider all finitely generated. Oh, this is finitely generated subframe. This is finitely generated. This is finitely generated subframe, right? Then for the disjunctive A clause, we have the following result. So law is valid here. Law is valid here. Law is valid here. Law is valid here. Then from that we can conclude in the full frame law is valid. So it's a bit like a compactness, right? So every finite generated subframe, we can say law is valid. Then the full frame law is valid. So it's also a bit like a disjoint union, right? So yep. Then so actually this is the proposition for any frame F and disjunctive A closes law. For all finitely generated subframe G of F, law is valid in G. Then we can say that in the full frame F validates law. And from that, we can say that every VA interdefined frame class F reflects finitely generated subframe. Okay, so then this is the main result of this talk. So And the elementary frame class F is VA interdefinable if and only if F is closed undertaking bounded multi image generated subframe. And it reflects prime filter extensions and finitely generated subframe. And the proof is somehow a combination of argument in Rodenberg and also argument in the my joint work Joni Wilteman. Here, I also use the Johan van Benten model theoretic argument. Okay, so this is the intermediate result. Okay, so now I can go into the final part and tell you what is the idea of increased logic. So here I want to give a team semantic for intuitionistic logic. So we already see that the idea of idealized mathematician, but the idea of team semantics is conceptually a bit different. So let M be an intuitionistic Kripke model. So we can still use the same Kripke model. And let's say that subset of T. I do not assume that T is upset or any subset is fine. This is a team. Then the semantics given as follows. So let's see one by one. So team T forces P. Then the T is subset of VP. Yeah, everywhere inside T, P is true. And the bottom, if and only team should be empty set. The conjunction is similar somehow. Conjunction is similar. But interesting point is disjunction. For disjunction is somehow the following. So we have here, let me write here. So we have chim T, right? Then we can split chim into two parts, and the overlapping is also fine. But here, for simplicity, I put the disjoint. This is T1, and this is T2. Then I can say this is phi true, and this is psi true. Then the for chim T forces phi or psi. So this is semantics of disjunction. So chim forces disjunction, then there's a way of splitting chim into two parts. T1 forces phi and T2 forces psi. And the implication. So implication is somehow we need to lift the accessibility relation of R into the level of chim or subset. Then the chim T forces phi imply psi if and only if we need to check all subchim S, and the subchim is taken from the R image of T. R image of T is defined in this way. So we need to collect all the W successor inside chim T. Then after that, this is a similar box implication. So S forces phi, then S forces psi. So these are, yes. Then what we can get is actually this semantics is somehow satisfy the following property called flatness. For any intuitionistic formula phi, we get the following equivalence. Chim T forces phi if and only if we can check all the elements of W. And here I use this one. This one is the ordinary Kripke semantics. So in this sense, if we just focus on the intuitionistic logic, we don't need to have a chim semantics. Somehow we can just reduce how the formula behave over the singleton set. And let's go to the next. Then now I want to add one special, this is the increased disjunction. Increased disjunction is defined, given semantics is defined as you expected, actually. For any interest Kripke model M, chim forces disjunction. Here I use the disjunction, right, in a meta level. And previously we use a splitting disjunction somehow. Okay, then, Then here I put one example. So now dependence atom can be defined as follows. So, and one thing what I can say is following. So I told you the question. So in this syntax, question is defined in this way. So for this part, we need to use increased disjunction. Then they want to say this is the formalization of question. This is somehow their syntactic sugar somehow. Then the dependence atom, if we use this syntactic sugar in the setting of dependence atom, definition of dependence atom, it becomes the following, right? So, and then the question Q implies question P, right? And the P is just become question P. So this means that and from this, they want to, so intuitive logician want to say that dependency is somehow captured by the implication between question. Anyway, so I can give you just one example. So this is the W is the biggest gene, right? Biggest gene for domain. The force is P, include disjunction, not P, if and only if. You can believe this relating. Everywhere P is true or everywhere P is false. So like P behave like constant. Okay. Yeah. And the flatness property fails for formula with increased disjunction, but still we can have a persistency property. So gene T force is phi, and S is subset subgene of R image of T. Then the S force is phi for any formula phi in the increased disjunction. Okay, so then the now question, how we can define the notion of validity. So of course, validity, I want to consider every gene, right? Every gene. But we can have a nice definition. As you can see, we can go this way, right? This is just application of universal quantifier. You can just, as a T, you can just take W, right? Then this direction is easy. Elimination of universal quantifier. How about this direction? Actually, then I'd like to note that this is a this is the same as R image of T. This is also easy. Then now we have a persistency property. So persistency property allows us to move this direction together with this result. Then these two become equivalent. So this means that for defining validity, I want to say the phi is valid in F. Then we can just check the biggest gene, W, for all variation B. Then based on this notion of validity, we can define inquiry definability by a set of formula from formula with increased disjunction. Okay. So so now I want to connect a formula with increased disjunction and VA into definable class. The key observation is the following. So everywhere P holds and everywhere not P holds, and P increased disjunction not P defines, actually both formula define the same property. Everywhere is reachable. And once I realized this, I was wondering how I can generalize this result to arbitrary formula. And it's possible. So equidefinability between the formula with increased disjunction and VA disjunctive A clauses. So first lemma is formula for any finitely many interesting formula and the model. We have the following equivalence. So this is sorry. This phi I is the same. Basically, idea here is that this formula is valid here. Then this formula is valid here. So basically, the increased disjunction can be mimicked by the interesting disjunction of universal modality. Yep. Then our goal is proving following equidefinability lemma. So for any class F of frame, I want to prove the following equivalence. F is VA into definable, F is into I definable. So then the easy direction is from up to down, because so once you have such a shape of formula, by using this lemma, we have a formula with increased disjunction. So up to down is just one application of bridging lemma. Then how about down to up? Suppose that f is inq definable. Inq definable. Inq definable means, so this is very nice shape, right? So this is just a formula with inquisitive, intuitionistic formula, and the inquisitive disjunction just only this part. So, but if it's inq definable means we may have an inquisitive disjunction somewhere. I don't know how they have a nice position or not. So, but actually there is a nice result, normal form result for every formula phi possible with inquisitive disjunction. There are finitely many intuitionistic formulas such that phi and inquisitive disjunction psi I is a interesting formula become equivalent. So there's such a nice normal form result. Then if we, this is the formula. Maybe I should. So we have this, and then this each formula by using this normal form result, we can change this part into such a nice shape. Then we use this normal bridging lemma to hit this set of disjunctive A clauses. And this finish to prove the bottom to up. Yep. So this is main result. So and this is intermediate result. And but now I can change this VA int part into inq I. So somehow this finish to the main result. But some of you may be interested in the concrete example, but just skip. And if you are interested in, please, I'm happy to show this later. Conclusion, further direction. So basically, in the first part, I reviewed the several Gold-Thomason theorem, but the key thing is I really like a van Bentham model theoretic proof. So for the intuitionistic, for example, dependence, model dependence logic, it does not close undertaking a uniform substitution. So I don't know how we can give a nice algebraic treatment, but we can still use the van Bentham, the purely model theoretic argument. The key observation in this talk is inquisitive disjunction can be mimicked by using intuitionistic disjunction and the universal modality. And I didn't say that this particular syntax can be regarded as intuitionistic logic with positive occurrences of A. And now I'm working with this question with Joni Wilteman, and our answer is positive. And we may also consider relative definability within a finite frame. We may use a notion of Yankov-Fine formula to get this result. And the third question is related to the Mofua's question, so character model definability. Actually, Goldblatt provided the characterization of intuitionistic models. And I may consider the same question with universal modality and positive occurrences of universal modality. Then how about the algebraic proofs? We may try. And how about intuitionistic model logic or inquisitive intuitionistic model logic? Anyway, that's all my talk.
Many thanks,